Hello everybody, this is Carl Kirkconnell from West Coast Solutions, and I will be presenting the integration of a tactical cryocooler for a 6U hyperspectral thermal imager. I have the privilege of presenting this work that was performed by a large team of excellent folks and excellent organizations, and see some of the names of my co-authors: Miguel Nunez, who did a tremendous amount of work in helping me pull this together, Ingo Rulik from AIM, Mark Zagarola from Criari, and Don Rafal from JPL. So I want to thank my co-authors and thank those organizations for the privilege of presenting this work today. Okay, so the high time mission, we're going to start at a high level here. We're going to start by a discussion of the mission, then we're going to get into the spacecraft, and then we're ultimately going to bore down into the cryocooler arena. But as you can see, if your eyes have already gone to the bottom, how we are going to tie the enabling of these technologies into the cryocooler system itself. So moving back up to the top. So this is a high spectral and high spatial resolution long wave infrared spectrometer, and the missions that we are after, capabilities that we are demonstrating with this system, involve characterizing evapotranspiration, volcanic degassing, and urban heat pollution, and we'll show you a few examples in the charts to follow. This has been done, but what is really unique here is it is now being done on this program on a 6U CubeSat platform. So this is a lot of capability to try to jam into that very small form factor. The thought here is that this is an initial demonstration of a single flyer that will ultimately pave the way for a constellation with this kind of capability. And obviously with the constellation comes a more strategically relevant and more scientifically valuable revisit rate. But we're starting with the single flyer for this project. So the key technologies, and these are identified at the program level, not by the cryo guys. These are the three that have been highlighted. Number one, a no moving parts Fabry-Perot imaging interferometer. So this is what allows the LWIR spectral imaging, and it does it in a compact package. Everything about this program is about compactness to fit within that 6U format. Number two is a novel barrier infrared detector focal plane array. This is the key technology piece that the JPL folks are bringing to this. And as you can see, the claims, the high signal to noise ratio, uniformity, temporal stability, all operating at a relatively high operating temperature. Again, that ties back to the 6U because of the required power to get to colder temperatures. And then finally, the onboard processing. There's just a tremendous amount of data that's produced from these spectrometer type systems. We're not going to really spend too much time on that today, but I did want to note it. And also note that, as I stated right at the beginning of this chart, the number one and number two are the optical payload, and those are enabled by this AIM Criari cryocooler system that we're going to be talking more about. This next chart is on the science mission itself, and there's a lot of information on this chart. This would not have been an appropriate chart probably for the in-person conference, but this unique format gives us an opportunity to do things like this. So I wanted to give you all this information, give you the opportunity to digest it yourself offline. I'm going to talk to just a couple of the key points here. We see the different technologies here are kind of walked through with the focal plane. You can follow through down with the paragraph here and see how each of these different pieces map into each of these key components. I do want to highlight this IDCA. This is just an example of an IDCA. So you're going to see some images of our IDCA in a little bit, and it's going to look different. But this good background information just to give you a sense of the key components that are comprising this instrument. Some good information over here on the right. Here we see the sort of imagery that we're going to get here. This is a spectral instrument, so we're looking for these kind of spectral signatures going out to a very high, a very long wavelength, 10.7 microns, which is a pretty impressive capability, particularly on this 6U format. And you'll see a focus here on the volcanic emissions aspect of the capability of this instrument, and it's understandable that that would be a focus for our good friends over in Hawaii. The team roles here. Now, this is interesting because the team here has really been as much as anything also driven by this 6U form factor. The key folks in the beginning, the co-primes on this are the University of Hawaii, the Hawaii Space Flight Lab group, and JPL. And beyond that, the rest of the team has kind of been fleshed out. And it's been fleshed out in accord with these criteria over here, the component selection and vendor selection. So when you've got this 6U format, that's the first thing that pops to the top when you're looking at any of the different component technologies. That's etched in stone. Things can only be so big. So whereas you might normally expect to see the requirements above the volume, in this case the volume is the key requirement, and then it drives down from that. So all the different component selection, not just the cryocooler, but we're particularly talking about the cryocooler today. This is the order of priority that the Hawaii Spaceflight Lab folks define. First of all, you got to fit in the 6U form factor. Then of course you have to be able to satisfy the mission. Reliability. Now, even though it was a short mission with just one flyer, it's got to work. And so we wanted to go with higher TRL technology where available. And then, of course, the lead time for delivery and cost. Now, the program schedule has been stretched out a bit by COVID, but it still needed to be done in a fairly short period of time. And also to stay on budget. This is a NASA Invest funded activity, so it's got a decent budget, but it's not infinite. So where this led us to on the cryocooler subsystem was the rest of the folks that you saw on my authors list on the first chart. So first of all, of course, myself speaking on behalf of West Coast Solutions. We're essentially the cryocooler systems engineer on this program. And the AIM SF070 cryocooler you're going to see in a little bit, that was the thermomechanical unit that we selected, and you'll see why to follow. And then Criari is bringing the cryocooler control electronics. This is a collaboration. Criari and West Coast Solutions do a lot of work together in this area. And this is a two-board solution. One, the main controller. The second, the input ripple filter. And you're going to see that also presented in charts to follow. So the key drivers, there's obviously a long list of requirements associated with this instrument. I just grabbed a few of the key ones with the support of Miguel. And the big driver at the top for the optical payloads, of course, the GSR 60 meters at LWIR wavelength, 25 spectral bands. I highlighted in blue these requirements that start to really flesh out what we want for the cryocooler. Focal plane needs to operate in the 69 to 72K range. We're trying to keep the warm end below 40 degrees C. The TMU is certainly capable of operating reliably at higher rejection temperatures, but we had a sense going in, of course, that we were going to be power constrained, and our wet finger in the wind was that we needed to keep that rejection temperature below about 40 C in order to be able to keep the input power into a tolerable range. Interesting to note that with this IDCA arrangement, that with that dewar tied in to the warm end of the expander, higher heat rejection temperatures also increase your dewar parasitic heat load, which further increases the power. So you can get kind of a runaway situation here. So this less than 40 degrees C rejection temperature is a big driver. The lens temperature isn't really so much a driver for the cryocooler selection. The pixel blur is indirectly. The mission analyst did quite a bit of work and determined that active vibration cancellation was not required. We did take some integration measures to mitigate exported vibration, as you'll see, but active vibration cancellation was not a requirement. Here is the entire 6U, and I don't have an hour of your time that I think you would be willing to give me to go through all of it. So we're going to focus in certain areas here. Again, just a lot of good information though for you to take away and study at your own time to the extent that you're interested in the subject matter. We're going to focus over here on the payload and in particular over here on the cryocooler subsystem. So if you take a look at the whole 6U, just to kind of orient you a little bit, here's the optical payload. You can see the lens right here. We're going to be talking about the heat rejection from our system and how we're using the top and bottom panels. So there you can see, I'm going to point with with the mouse here. That is the top of one of our thermal straps dumping to a radiator. There's also one that goes down to the bottom. And so the discussion that we're going to be having is going to be in this area here with the optical payload. And then if we come down here, we've broken out the IDCA and the key cryo components. And you can see those a little bit better over here. So here we have the SF070 cryocooler kind of disappearing inside of clamps and thermal straps and whatnot, but you can, I'm sure, visualize how it fits in here. And then we've got our two cryocooler electronics boards. We've got the main control electronics. We're going to talk about the Criari MCC ETS and some charts to follow, but you can see it here with a thermal rail, and obviously it's going down to one of the facets on the bottom here. And then here's the input ripple filter, and you can't see any of the action. It's all on the other side of the board in this view. So this is just looking at the back side of the board. But this is where they sit, and if you go back to the prior chart, you can see where that fits within the whole 6U. Important to note that this combination has already been successfully tested. So at West Coast Solutions back in the October timeframe, we have an earlier version of the MCC ETS, an unmodified version. I'll talk to what that exactly means and some charts to follow. It's highly representative. We have the actual brass board for the input ripple filter that was developed for this program. And we have an SF070 cryocooler. So we put these all together and we've tested all these, and it was without complication. Okay, let's dive in a little bit deeper on the cryocooler itself. So the cryocooler is an SF070 and it is in an IDCA. So it really just so happened that the AIM SF070 fell into a sweet spot for us here. It ended up being a very good fit, giving the temperature, the 70 Kelvin temperature, the estimated 300 milliwatt heat load requirement. There was a decent amount of uncertainty with that number coming into the program, so we wanted to make sure we were beating it with margin just in case. And the mass of the cooler was attractive at 850 grams given this amount of cooling capacity. And very importantly, and as noted on a prior chart, it had to fit within the 6U bus. And so it was about at the limit of what we could have fit within a 6U bus. It's tight, and you probably already have that sense from looking at those images before, but it does fit. It does meet the cooling requirement, and it does it with adequate margins so we can be comfortable going forward. Here's the cooler and some rough dimensions just to orient you. And here it is in IDCA. So we're going to talk about that next. So the integrated Dewar cooler assembly. So this is an interesting choice that's made for some of these low-cost space missions. It seems a little bit odd to fly a vacuum in a vacuum, space in a vacuum in the vacuum of space, but it does allow for a great deal of simplification of ground testing. You can test your whole optical payload as you're going to fly it. And so that was the approach that was taken here, and you'll see how we're taking advantage of that in the charts to follow as well. So this capability to do a full instrument checkout on the benchtop without having to go into TVAC is a big cost savings. Next integration challenge. So as I mentioned before, active vibration mitigation was not a requirement, but we did want to use a cooler that was naturally low in vibration. So we picked one of these dual opposed piston compressors as opposed to a single piston compressor or a rotary. And we located the compressor as close as possible to the geometric center of the spacecraft itself. So then you again can refer back to the prior charts to take a look at how that ends up driving the whole packaging scheme. Now, the one thing I would note is that the tactical coal finger is just not ideal for a space application, particularly here at the warm end. And obviously these things are typically used in terrestrial applications, and you can bolt that to a big heat sink and put some fans blow across it, and it works. They work great, and their high tolerance for high rejection temperature plays in well there. So it's a perfectly fine scheme for terrestrial air-cooled applications. It can be challenging for a space application, and indeed that has been a focus of the challenge going forward. Last thing to note here, this particular blowout down here, the Dewar integration is being done by Ayers. If you're familiar with Ayers, they do a lot of this work with AIM and packaging their coolers into IDCAs. And we're doing a lot of the initial checkout with an AIM DCE 100. This was also a nice testability feature. It gave us a way to use the off-the-shelf COTS electronics to keep moving forward with the integration while we're waiting on the build of the new electronics from Cryori. Okay, I mentioned the integration and heat rejection scheme was a challenge, and that's what this chart is all about. So starting up here in the upper right, this is kind of the key here. So what you're looking at here is a slice through the side. Here's the IDCA. Here's the warm end of the expander. And what we're trying to do is just get the heat up to the radiator and down to the radiator. Use both sides, so no matter where we are in the orbit and the sun hitting what surface and Earth IR and albedo, we'll always have a decently cold radiator to carry the heat load out. And then the compressor, you can't see it as well here, but you can over here. How it's also tied to the radiators. And we've got these mount points, same three mount points, top and bottom. So sticking over here with this view, now getting to some of the details, you see a clamshell arrangement around the compressor. We really weren't battling mass too hard on this program. It really was just volume. So this is pretty massive structure to minimize the thermal losses in the heat rejection path, and that worked out just fine. The expander is a much more interesting challenge here. What we have, and it's a little bit difficult to make out, but there's a copper clamp that clears around this knob on the back of the expander. So we're making contact with the back flange here and with that knob. And that interface is filled with a Bergquist gap filler. It's an interesting material that's injected into that gap, and it acts like if you're familiar with any of the thermal interface materials, the Bergquist gap pad. It's just a different form factor, but when it cures, it's essentially the same kind of material. So that's how we get the heat from the expander into that clamp. And then we got to get the heat from that clamp out to the radiators, and we're doing that with some graphite foil straps. This was not really a mass play, it was really more a volume play. And so rather than going with the more conventional copper and aluminum, we really needed to get a more efficient, volumetrically efficient thermal straps. We went with a more aggressive graphite foil technology, and we're using a NeoGraph, it's called eGraph thermal interface material at the interfaces at both ends of this strap. Last thing I note, we have this support bracket here. Now this isn't part of the thermal feature, but this bracket holds the Dewar really via the back end of the expander, so that it doesn't move relative to this payload bench plate. So that's what this support is about. So we have flexibility here in the straps, but a rigid mount right here, so that this whole IDCA is held off of this payload bench rigidly at multiple points, both here and over here, so that it doesn't move. And then we have the flexible links that take us out for the heat rejection. Okay, we've talked about the TMU. Now we're going to talk about the cryocooler electronics, the rest of the cryocooler subsystem. The cryocooler electronics consist of two boards, a main controller, and the input ripple filter. And we're going to take them one at a time. The main controller is a variant of the Cryori micro cryocooler control electronics for tactical space, MCCETS. And there is a paper that Cryori is presenting on Thursday on this very subject. So I'll touch on it only briefly here. So this is the first set of cryocooler electronics that's been developed, certainly that I'm aware of, that is really optimized for this new space LEO environment, where cost is an aggressive target. You really need a design to cost mentality to be successful. But there is a certain level of radiation tolerance and mission assurance that's required that goes beyond the typical tactical cryocooler electronics arena. So MCCE has sought out that need in the market. An adaptation of it's being used here. The SFO70 only requires one motor drive circuit, and we took advantage of that here. We took one motor drive off of the board, and it does help meet mass. As I stated before, the mass for the whole payload, the whole spacecraft, was not too much of a driver, but it did help us fit in that 10 by 10 centimeter envelope with a little bit more comfort, and at the same time meet the mass allocation that had been flowed down to the MCCETS. Ripple filter is a custom board that's been developed for high tide. It's very similar to other ripple filters that West Coast Solutions and Cryori have developed, so it's not completely novel in that regard, but it was customized and optimized for this particular power level, these frequencies, this packaging. So it really was a bottoms-up design, but one well informed by the past. The brass board's been developed by West Coast Solutions. As I mentioned earlier, it's already been built, tested, integrated, and now the flight packaging and flight build is well underway at Cryori. So all in all, we have 2 circuit boards. Each fits within an envelope that's less than 10 by 10 by 2 centimeters, and the total mass for these 2 boards is less than 500 grams. What you're looking over here at the right is an earlier version. This is probably an image you've seen in prior publications, but from the very beginning, the perspective on the MCCETS was that it was going to see opportunities in CubeSats. And here you see an earlier version of it fitting inside the facet of a CubeSat frame. Next subject we're going to cover is the benchtop testing that's going to be performed at Jet Propulsion Laboratory. Earlier on in the program, we were talking about TVAC versus no TVAC and taking advantage of the opportunity we have with the IDCA to do benchtop testing versus the additional value particularly for the heat rejection system of going up to the full vacuum level. Well, that question kind of got answered for us with COVID. So just like this conference, this program was affected by COVID, and this 2-person rule at JPL for TVAC pretty much made TVAC testing an impossibility. So we are taking advantage of the IDCA architecture and doing a very thorough checkout at the benchtop level. Now, the primary purpose of this testing at JPL really is optical. They're the focal plane experts. They're the one that are bringing that technology to bear here. And you can see the list of tests that are going to be run over here at JPL. The focus here, the temperature drift and stability. This is really the toughest test, and this is a key performance test. So this is the focus of this activity. But as the cryocooler system integrator, I can tell you that it's very nice that we're going to be able to get a good thermal test out of this. There's really just a few non-flight features as it relates to the cryocooler subsystem. Obviously, we've got these fans and radiators here instead of the spacecraft radiators. That would be the panels of the 6U bus. There's a test fixture, of course, to hold everything. And then we're using the DCE 100 to drive the cooler in the absence of the Cryori electronics, which are coming at the first of the year. But we've done a ton of testing at West Coast Solutions with both the DCE 100 and the MCCETS, and we have no regrets in that area. And given that this is highly thermally representative, certainly in a way that can be mapped back well to the overall thermal design and thermal model of the system, the fact that the JPL folks are going to be taking a bunch of system temperatures and measuring component powers is going to be very helpful for us for the thermal design characterization, as well as for the correlation of the thermal model. So we're on a wrap-up chart here. Thank you all for bearing with me. I went a little bit longer than what I had intended, but hopefully this information has been helpful to you. So in wrap-up, this is a long-wave infrared hyperspectral instrument on a 6U satellite. We are going to be doing 70 Kelvin cryocooler operation on this 6U. I'm not aware that that's been done, but there's a lot of stuff that's happening these days, but I think this might be a first. I might be informed differently during this conference, but I think that's the case as I sit here right now. We are entering the initial stages of the payload integration. It's a very exciting time on this program. So the IDCA has already been integrated at AIRS, and they're going to soon be delivering that to JPL. And then JPL is going to conduct that set of tests that I just showed you on the prior chart. And then early in 2021, that payload is going to be going over to Hawaii. In parallel, Cryori is completing the buildup of the MCCETS variant and the ripple filter. We've already brass boarded all this stuff out, as I noted before, but certainly from the perspective of the cryocooler subsystem team, folks on this on this paper here today, this flight integration and test is an exciting milestone, and that's going to occur early in 2021. And then by late 2021, I don't have exact dates here, but we're projecting to launch. So this is an exciting time for this program. 2021 is going to be an eventful year for it, and I look forward to reporting some additional progress and hopefully some on-orbit operational characteristics in the future conference to come. Thank you for your time.